So I will talk about what cluster algebras have to do with the dimer model. So Pavel already introduced cluster algebras in the previous talk, and today we'll see why this is relevant to this conference. So the first thing is, anytime you have a bipartite graph on a surface, so in the dimer model, you're studying bipartite graphs on surfaces. So if you start with a bipartite graph on a surface, you can construct an ice quiver from it. Usually we're interested in either the disk or the torus. These are the ones that appear most commonly, but you can do this on any surfaces with boundaries. And so here is an example. So the quiver is essentially the dual graph of the bipartite graph. So suppose this is a disk, and suppose we look at this bipartite graph over here. So I have some vertices that are on the boundary of the disk, and some vertices inside the disk. So this is going to be white, and this is black for me. So this is a bipartite graph embedded in this disk. And from this bipartite graph, you can create a quiver by placing a frozen vertex at each boundary face. A mutable vertex at each internal face. And then connecting vertices such that white is on the right. So anytime you have an edge, you have two faces on either side, and you draw an arrow like this such that the white vertex is on the right. You could use either convention, so you could also use the other convention, but yeah, it doesn't really matter. So for each of these boundary faces, we're going to have a frozen vertex. And each of the internal faces is a mutable vertex. And you connect them according to this rule. So here you want to go this way, and then here it's like this. So you know that the arrows have to alternate in orientation, so it's going out, coming in, going out, coming in. So we don't need to know the other colors. So I think I drew all the. So you don't draw arrows between the frozen vertices. So we don't need to draw these arrows. And this would be the quiver in this example.
In the bipartite graph, you only have like degree 1 vertices on the boundary. Is that an assumption, or is that not necessary?
So that's a convention that people commonly use, and it's nice to have that assumption. But things still work if you don't have that assumption. Are there other questions? Okay, so in this way, starting with any bipartite graph, you can produce a quiver, and then you can ask what is the cluster algebra of this quiver. So Pavel talked about the cluster algebras you get from looking at triangulations of polygons. So if you have a polygon and you take the quiver that you get from this triangulation, then the cluster algebra is the coordinate ring of the Grassmannian. Is the coordinate ring of this Grassmannian. And this picture actually generalizes this story. So because these quivers that you get from these triangulations You can also write them as quivers that you get from bipartite graphs, except the triangulation doesn't generalize. If you want to study general Grassmannian, so if you have GKN, where k is something other than 2, then you cannot use these triangulations, and you get these quivers. So the cluster algebra of this quiver is the coordinate ring of the Grassmannian 3, 6. So this is due to Jean Scott. So this is one example of how, looking at bipartite graphs and surfaces, you get interesting cluster algebras that have, where the algebra has a natural meaning. It's the coordinate ring of something geometric. Okay, any questions about this example? So you could also look at quivers that you get on other surfaces. So here is a quiver that lives on a torus. So let's look at this bipartite graph over here, which is composed of a bunch of hexagons and a bunch of squares. So this is an infinite bipartite graph which lives on the plane, and it's periodic in both directions. So this is an infinite biperiodic graph. And to this graph, you can associate a quiver, which looks like this. So suppose these are my white vertices. Then the quiver looks like this. So this face is a translate of this face. So let's give them the same name. So this is going to be phase 2. This is going to be phase 3 for me. And these are going to be phases 1 and 4. So all the phases are translates. And then to this bipartite graph, I can associate a biperiodic quiver, which looks like this. So I want the other color. Yeah. So I have a quiver that looks like this. And now, I can look at what this quiver looks like on the torus. So I have 4 vertices, 1, 2, 3, and 4. And I look at how many arrows I have between each of these vertices. So I have an arrow between 1 and 4. So I have an arrow like this. Between 2 and 3, so I have 3 arrows that go from 3 to 2. Right, so there are 3 translates of the phase 2 to which I have arrows. So when you're looking at this on the torus, you're going to get 3 arrows from 3 to 2. Yeah, you're right. Oh. Yeah. Yeah, you're right. So maybe I want to change the names of the faces at some point, but let's see. So let's draw the whole quiver. So from 3 to 2, I have 3 arrows. From 1 to 2, or from 2 to 1, I have 2 arrows. Yeah, I think I want to change 1 and 4. So this should be my. Okay. So now the arrow is from 4 to 1. And then from 1 to 3, I have 2 arrows. So 2 arrows like this. From 3 to 4, I have an arrow like this. And between 1 and 2, I have an arrow from 1 to 2. And from 2, I have 2 arrows to 4. Yeah, I feel like I messed up something because, yeah, I have 2 outgoing arrows. Okay, yeah. Yeah, no, it's right. Yeah, I had one of the directions wrong. So if you do this correctly, you should get this quiver over here. And this quiver is called the Sawmorse 4 quiver. Except this is a quiver that comes from studying a bipartite graph on a torus. And the quiver is naturally embedded inside a torus. Okay, so any questions about this? All right, so let's recall what mutation was. So once you have a quiver, you can mutate it. And the rule was as follows. So you have a bunch of steps. So the first step is to introduce shortcuts. So suppose I'm mutating at a vertex k. Then for any sequence of arrows like this, you introduce a shortcut, I to k, I to j. And then you reverse the orientations of all arrows. At the vertex j. And the third step is to remove 2 cycles. So let's apply that process to this quiver over here, where I want to mutate at this vertex over here.
The second point is you reverse orientation at arrows at k.
Oh, yeah, at k. Thank you. Yeah. So let's apply this mutation process to this quiver over here. So what do you get? So in the first step, so let me redraw that quiver. Okay, so this is my quiver, and I want to mutate at this vertex. So in the first step, you look at all arrows that go into 1 and come out of 1. So I have 2 to 1 and 1 to 3. So I get 2 arrows like this. I'm missing. And then I have 4 to 1 and 1 to 3. So I get 2 arrows like this. And that's it. So that's what you get at the end of the first step. And then the second step is to reverse the orientations of all arrows incident to 1. So this arrow now goes in the other direction. And this arrow goes in the other direction. And these two arrows go like this. And finally, I have to cancel out all 2 cycles. So I have 2 arrows going this way and 2 going down, so I can cancel them out. And I get this quiver over here. So if this was Q, this was mu1 of Q. So do you notice something interesting about this quiver? Yeah, that's right. So this quiver is a rotation of the one that you started out with. So if you take this picture and rotate it by 90 degrees this way, then you're going to get the quiver that you started out with. So this process is an automorphism of this quiver. And you can look at what happens to the underlying mutation. So you have cluster variables for each of these vertices of the quiver, or each face of this bipartite graph. And when you apply this mutation, you're going to get a new x1. So x1 prime is going to be the number of arrows, the product of all cluster variables where you have outgoing arrows, which in this case is x3 square, plus the product of all cluster variables where you have incoming arrows, which is x2, x4. And all the other cluster variables are exactly the same. But now if you apply this rotation, that corresponds to rotating the cluster variables. So what this operation gives you is a map from the initial cluster variables to a new set of cluster variables, where I've shifted the indices to rotate the quiver. So what used to be 1 is now 2. And the last one, which you can think of as x5, is this quantity. And now you can iterate this map. So now you mutate at vertex 2, and then at vertex 3 and vertex 4, and so on. And this gives you an interesting dynamical system, which starts out with a bunch of quantities, and then you keep iterating this map over here. So this dynamical system is integrable, and it's an example of something called a cluster integrable system. Of Goncharov and Kenyon. And you will see more of this in Sanjay's talk. So this sequence, so if you initialize all these variables to be 1 and keep running this sequence, so you keep applying this map, you're going to generate an infinite sequence of numbers. And this is called the Sommer's 4 sequence. So this is a sequence of numbers that comes from number theory. Sommer's was studying elliptic curves, and he was looking at, so an elliptic curve is a group, and you can keep adding elements of the group to a point. And he realized that as you keep doing this, you generate a sequence of numbers that are all integers. Although, if you look at the formula, there is some division involved. And this is because of the Laurent phenomenon for cluster algebras. And again, the fact that this comes from translations on say again?
So why is Laurent phenomenon good? Because you're dividing by ones, right?
Yeah, so in this case, you're dividing by ones, right? So, so if you have a Laurent, right, so each cluster variable that you're going to generate by doing this is going to be a Laurent polynomial. And yeah, in your denominator, you always have a monomial in x1, x2, x3, x4, and that's always going to be 1. So this is going to generate an integer sequence, although you have divisions in it. Okay, other questions? So the fact that this comes from these elliptic curves is also related to the integrability of the sequence. So the elliptic curve would be the spectral curve of this sequence.
So maybe behind that correction.
Yeah.
Met Thomas, he didn't study any elliptic curves.
You did not? Okay.
He just studied sequences, and he computed a lot of sequences.
But, okay, so then the connection to elliptic curves was made later?
Yes.
Okay. Yeah. Okay, thank you. Okay, so this operation of mutation also has a natural interpretation in terms of bipartite graphs. And it was kind of independently discovered before mutation was discovered. And it looks like this. So in the bipartite case, you're only allowed to mutate at degree 4 vertices. So a degree 4 of the quiver. So a degree 4 vertex of the quiver looks like a square face in the bipartite graph. So something like this. So the quiver of this square face is going to look like this. And now, if you mutate this quiver, you're going to get this quiver over here. So first, you have to introduce shortcuts. So you get an arrow like this, and an arrow like this, like this. And then you have to reverse the orientations of all arrows. And you get this quiver over here. And the bipartite graph associated to this is the dual graph. And if you use the convention that white is on the right, then this should be a white vertex. This should be a black vertex. And you get this graph over here. So this is something that if you've seen dimers, you would recognize. This is urban renewal, or the spider move, or the square move. So mutations at degree 4 vertices, if you think in terms of bipartite graphs, is the following operation. You remove a portion of your bipartite graph that looks like a square, and you replace that portion with a spider, with this picture over here. But there is one more move that you need in the story of bipartite graphs, because when you look at mutation, you have a third step, which is to remove 2 cycles. So removing 2 cycles is also something that you're probably familiar with. So in terms of bipartite graphs, it's the following operation. So what's a 2 cycle? So if you have a 2 cycle in your quiver, then that corresponds to a degree 2 vertex in your bipartite graph. So something that locally looks like this. And if you remove it, then you're replacing that picture with this one over here. So everything is the same outside this little disk, and inside you contract this 2-valent white vertex into a single vertex. And then these arrows go away. So doing mutations on bipartite graphs is the same as doing urban renewal along with this operation of removing two valent vertices. Okay, any questions about any of this?
So what happens if you do mutations on something with other than degree 4?
Then you're going to usually not get something that is the dual of a bipartite graph. Like it would not be the dual of something planar.
Can you write down what the seeds would look like when you do this transformation?
Yeah, so for each of these faces, you would have a cluster variable. Let's just call it ABCD. And then this would be E. And what happens is, so these are the same. And this cluster variable is going to become something new, which is this. Yeah. Any other questions? Okay. Okay, I don't need this most. So Pasha mentioned this theorem of Fomin and Jelinsky that every cluster variable is a Laurent polynomial. So every cluster variable is a Laurent polynomial in the initial cluster variables. With positive coefficients, with positive integer coefficients. And anytime you see something with positive integer coefficients, it's natural to ask, is this counting something? And I'll give you an example where it's counting something that has to do with dimers. So we want to look at the big Laurent polynomial you get by doing a bunch of mutations. And you want to say what are the monomials that show up in this Laurent polynomial. So this works more generally, but we are going to look at the example of the Aztec diamond. So the Aztec diamond is this sequence of graphs. So the diamond of size 1 is just a square. The diamond of size 2 is this picture over here. So each of these is a subgraph of the square grid. And then the diamond of size 3 is this picture over here and so on. Now, each of these being a bipartite graph, which you can think of as being a bipartite graph in a disk, has a quiver associated to it. And you can do mutations in this quiver. We are going to do a specific sequence of mutations. So first, let's look at this example over here. What we are going to do is, mutations in terms of this bipartite graph is happening at faces. So I first mutate at these faces. And then I get this picture over here. So I start with this picture. And then I mutate these faces. So each of these faces gets replaced with a spider. and I would get this graph over here. And now these are degree 2 vertices that you want to contract. So once you contract these degree 2 vertices, you're going to get this picture over here. So once I contract these, this thing becomes a square. So that's the square over here. And then you have the 4 neighboring squares. And these have legs. So I get this picture here. And now I do another mutation. So when I do this, I get new cluster variables at all of these faces. So let me give names to these cluster variables. So initially, I start out with some cluster variables on this guy. So let's just call them A, B, C, D, E, F, G, H. Okay, so I have some initial cluster variables. And as I did these mutations, I get new cluster variables in this guy. So these ones are the same as what they used to be. Except I, J, K, and L get replaced by some new cluster variables. So this is going to be some I prime, which is AM plus BH over I. This is going to be J prime, which is going to be BD plus CM over J. This one's going to be K prime, which is DF plus ME over K. And this is going to be MG plus FH over L. Okay, so once I did this first round of mutations, I get these cluster variables. And now I want to mutate at this face over here. And when I do this, I'm going to replace this square with a spider. And I get this picture over here. And this is where I stop. So now I have no more mutations that I can do. So I can mutate at this square face, but that's going back to this picture because mutation is an involution. And these are all hexagonal faces, so I can't mutate there. So the cluster variable of this face that I end up with is going to be something pretty complicated. So it's going to be, so this face was called M. So it's going to be J prime, L prime plus I prime, K prime over M. And the question is, if I look at this as a big Laurent polynomial, what is it counting? So let's expand it and see what this actually looks like. So I prime is AM plus BH over I, and then times K prime, which is DF plus ME over K plus mg plus fh over L, bd plus cm over h, j, divided by n. So this, when you simplify this, is going to be a big Laurent polynomial. Let's write down some of the terms. So if I multiply these expressions together, then I get AMDF over IKM plus AM square E over M plus plus so on, so 4 more terms. Okay, so you get this big Laurent polynomial over here. It has 8 terms in it. And you see that all the coefficients that show up are +1. And the question is, can you interpret this as some kind of generating function for some object? So what is the meaning of the monomials that appear in your big Laurent polynomial? Okay, any questions about that before we state the theorem? Okay, so before we state the theorem, there's another way to think of this process. So this was originally called the octahedron recurrence, the process we did. And the reason for this is, say you're looking at mutation at one of these square faces. So suppose this face over here. So I, B, H, M. So what you want to do is think of these faces as living at some level. So you have a lattice where A, B, H, and M are. So this square lives at, say, at some height, say 2. And this face I lives one level below, so say at height 3. So I is here, and B, H, A, and M are here. And you want to think of the new cluster variable you get by mutating at that face, so I prime, to be living one level above, so at height 1. And you want to think of this picture as placing an octahedron. So if I join these vertices to each other, then I have a square which lives at height k. And then I have 2 vertices that live below and above. And if I join these vertices, then I get an octahedron. Which has these vertices. So I prime, B, M, H. So one way to think of what we are doing is we start with the Aztec diamond, which is at some height. So some of its vertices live at, say, height 2, and the other vertices live at height 3. So these faces live at heights 2 and 3. And once you place octahedra, so this urban renewal transformation or the spider move can be thought of as placing octahedra at all of those squares. Once you place octahedra at these 4 squares, you're going to get things that live at height 1 and 2, and then you can place octahedra on top of that, and so on. And this process of doing mutations in this way is kind of building up a pyramid of octahedra. So it might help to think of a slice of this picture. So suppose you slice along this plane so that you don't see A and M. Then kind of what you see is your Aztec diamond at some height looks something like this if you just look at a slice. So things like, I guess this. So like B and H live at this height, and then I lives below. And when you place an octahedron, in the slice you see it as placing a square, and your I prime lives over here. And similarly, the other octahedra that you place, so you get a picture that looks like this, and you see a smaller Aztec diamond, and then you place another octahedron on top of that, and you get a cluster variable at the very top, and that's this one over here. So you can think of this process as completing this pyramid and asking what is the cluster variable at the very top. Okay, any questions? Yeah. This picture here. So this is supposed to be so I have the Aztec diamond, and I'm looking at a certain slice of it, like along this this line, and so I don't see. So I see like these variables, but I'm not seeing those. And so I'm just looking at a 2-dimensional piece of it, where you can see how this pyramid is being built up. So an octahedron, when you slice it, is going to become a square. So you're slicing it along like this plane, and you see a square. Are there other questions?
Where did you, how did you pick the variables you did for the level 2 on the slices?
So every other variable is going to be at level 2. So A, like all these guys are going to be at level 2. Not this K. Not the J. Yeah, okay. So these variables are at level 2, and the other, yeah, like the checkerboard pattern. I don't need this anymore. So the theorem is due to David Spire. That this cluster variable that you get at the very end by doing all these mutations, so top cluster variable, is a sum of perfect matchings of the Aztec diamond. So, weighted according to this rule. So every perfect matching has a weight, which is the product of the cluster variables raised to power 1 minus, the number of dimer covers on the boundary of that phase. So this cluster variable, the big Laurent polynomial that you're getting, each monomial corresponds to a perfect matching of the Aztec diamond. And there is some slightly strange looking rule for how you get the monomial from the matching. So let's look at an example. So I want to keep that, so let me remove this. So if you're looking at the Aztec diamond of size 1, then it's just a square. And you would mutate at this face over here, and you would replace it with a spider, and you would be done. So this is F. And the rule is that F is AC plus BD over E. So you have two monomials, AC over E and BD over E. And how many perfect matchings does this guy have? It has two perfect matchings. These two. And Spire's formula tells you that every cluster variable corresponding to a perfect matching should appear, so every face should appear the number of as many times as there are dimer covers around that face. So here you have one dimer cover around this face. So B should appear with power 1 minus 1. So this should be B to the power 0. C should appear 1 minus 0. So this is just C. So A should appear with 1 minus 0, and D should be D to the power 0. And what about E? So E should appear with power 1 minus 2. So you should have an E to the power minus 1. So the monomial associated to this perfect matching, according to Spire's rule, is AC over E. And that's this term over here. And by symmetry, you see that this has to be BD over E. Okay, any questions about this? So let's check a bigger Aztec diamond to see if we get one of those terms. So this is the Aztec diamond of size 2 that we looked at over there. So we had A, B, C, D, E, F, G, H, I, J. So let's take a perfect matching of this. So I'm just picking one arbitrarily. So this is one of the many perfect matchings of this guy. So what is the monomial that corresponds to this perfect matching? So E should appear with power 1. Let's go in order. So A should not appear because there is one dimer cover. B should appear with power 1. C should not appear. D should not appear because there is one perfect matching and you get 1 minus 1. E should appear with power 1. F should not appear. G should not appear. And H should appear with power 1. I should appear in the denominator. J should not appear. K should appear in the denominator. L should not appear and M should not appear. So the monomial, if I did this right, should be this one over here. And let's see if it's one of the, so, is it one of the monomials that I have on that side?
Yeah.
Yes, the last.
The last one.
Yeah, it's this one. Yeah, so it's this guy. Yeah, so that's one nice application of, or nice connection between cluster algebras and dimers, that sometimes the Laurent polynomials you get are enumerating perfect matching. So this works more generally than the Aztec diamond. And so the Somos 4 example that I showed earlier, each of the numbers that would appear in this Somos 4 sequence would be enumerating perfect matchings on some graphs. But they're more complicated graphs than the diamond. So this is the nicest example. Okay, any questions about this?
How big is the work for?
So I think it works for any, so this is a portion of the square lattice. So it's really also a graph on a torus like the Somos 4 one. And any graph on a torus has this Newton polygon. And I think Spire's result works in this generality of quadrilateral Newton polygons. So it's not completely general, and that should be an interesting problem. Like,
Terrence?
yeah.
I didn't hear the last sentence essentially. What did you say?
Oh, quadrilateral Newton polygons.
Quadrilateral Newton.
Yeah. I think.
Also work in the hexagonal lattice in some cases.
No, this doesn't work in the.
Not this, but you can have like a tetrahedron and like 2 hives on top and 2 hives at the bottom. Like, there's this paper of Knudsen, Tau and Woodward where they have a version of this for like pairs of hives. So you have pairs of hives, pairs of hives.
So I'm not familiar with this picture, but yeah.
I think the answer is yes, because I mean, you're looking at kind of a bipartite graph and a disk, and these will correspond to some Laurent expansions of twisted Plicker coils. And in effect, I think that's what Spare is doing here, because the Aztec diamond is that initial graph. The Aztec diamond can be seen as an initial seed for I forgot which Grassmannian. And when you are computing the Laurent expansion for this most central square, that will be the twist of whatever the Plicker coordinate is associated with that. And there's a general formula for that works even when you don't have squares.
Yeah, yeah, that's true. Okay, are there other questions? Yeah, so there's something that I never quite understood about the twists of the Plicker coordinates and this story, because these monomials are almost the same as what Spire has there, in the Muller-Spire paper, they have these monomials appearing, but they look almost the same as these ones, but they're not exactly the same. So there is some slight discrepancy, but it looks very similar. Okay, so I have like 25 minutes, is that right? Okay. So all of this story was about cluster variables of one type, and there's actually two different types of cluster variables that people study. So these are called A and X by Fock and Goncharov, and all of the story that we've seen about cluster algebras has been about the A cluster variables. So we've seen these A cluster variables. And these are the variables that transform like the Plucker relation or the octahedron recurrence. But there is another story which is kind of dual called X cluster variables. And this one is perhaps even more natural from the point of view of the dimer model. So the next thing I want to say is what are these X cluster variables and how do they show up? So they are both associated to the same data. So you have a quiver, except instead of having these A cluster variables at faces, you have a different kind of cluster variable at faces, which transforms according to a different rule. And the way this shows up in the dimer model, and we'll kind of discover what the rule has to be by looking at the dimer model, is as follows. So you have a bipartite graph. And in the dimer model, in the more general case, you would assign some weights to the edges of this graph. And you would study perfect matchings that are weighted according to these weights. So if you have a perfect, so this one doesn't have a perfect. Let's just say we have this graph. So if you take a perfect matching of this graph, so for example, this one, then you would assign it a weight, which is the product of the weights of the edges that appear in it. So this would get the weight G, F, E, H. And then you would put a probability measure on dimer covers according to this weight. So the probability of a dimer would be proportional to its weight. Now, there is an operation that you can do on weights that does not change this probability measure. So if you start with weights like this, and you take any vertex, and you multiply the weights of all edges incident to that vertex by a constant. So suppose you have a vertex with some weights around it, and you multiply these weights by some constants, then you don't change the probability measure, because every dimer cover is going to use exactly one of these vertices. So every dimer cover is going to use exactly one of these edges. And so the weight of every dimer cover gets multiplied by the same constant. And when you normalize, the probability measure is still the same. So this transformation is called a gauge transformation, because it doesn't change the dimer model. And so more natural than putting weights on edges is to look at the space of edge weights modulo these gauge transformations. So these edge weights themselves are not coordinates on the space of edge weights modulo gauge transformations, because they're not well defined. When you do gauge transformations, they change. So what are actual well-defined coordinates on this space? So here's the idea. If you look at any face, so suppose I look at this face over here. So suppose I call it 1. Then I can take the alternating product of weights of edges that appear around that face, such that, so say you go around the face in counterclockwise direction, and if you're going from black to white, the edge weight is going to appear in the numerator. So I can associate the following coordinate to that face, which is the alternating product of, so since I'm going from black to white along this edge, I have a D in the numerator, a C in the denominator, B in the numerator, and A in the denominator. So I get these expressions for every face. And these are gauge invariant because every vertex is going to have 2 edges that appear in this expression. So one in the numerator and the other in the denominator. So when you apply gauge transformations, they cancel out. Right? So if I did a gauge transformation at this white vertex, then I would multiply these edge weights by some constant. But because I'm taking this alternating product, they cancel out. So each of these is well defined on the space of edge weights modulo these gauge transformations. And so these are actually well defined coordinates. Except they're not actually independent because if you take the product of all the x coordinates for every face, you're going to have a relation which says that it's 1. So except you have this relation that the product of all. So these are the x cluster variables. So and you would have discovered them if you were studying the dimer model and you wanted to find gauge invariant coordinates. Okay, is the definition clear of the x cluster coordinate? Yeah. Say again? Yeah, so these are phase variables, are sometimes called phase variables because they're associated to the faces or phase coordinates. Okay, so how should these coordinates transform when you do mutation? So your mutation is this operation over here. And suppose you have some initial weights on these edges, which are defined modulo gauge transformations. I want to find new weights on the spider, which are also defined modulo gauge transformations. And after doing gauge transformations at these vertices, I can assume that these edge weights have been made into 1. And I want new A prime, B prime, C prime, D prime on this graph over here. And I want to choose this A prime, B prime, D prime, C prime, such that if you look outside the region where this move is happening, you don't see that anything has changed. So any event that does not depend on the edges that are involved in this move should not change if you replace it with this picture over here. So what that means is for any boundary connect, so imagine that this move is happening in a little disk. So these vertices are connected to other vertices that are outside the disk. And those connections remain the same. So you've only modified the graph in this little region over here. Now, what you want is, suppose you have a perfect matching like this that uses all the 4 boundary vertices. Then you have corresponding perfect matchings on this side that use all the 4 boundary vertices. In fact, there's only one on this side. while there are two on this side. So there is that one and there's this one. So you want to choose your new edge weights such that the weight of these perfect matchings is going to be proportional to the weight of the new perfect matching on the other side. So the weight of these perfect matchings is going to be AC plus BD. And on this side, you have 1, and you want these to be proportional. And the same for all other connectivities of boundary vertices. So this is one case. You have other cases. Another case is where you have a dimer here, and then these vertices are matched somewhere outside. Then you want to use both of these edges, and then these guys are still matched somewhere outside. So this perfect matching has weight A, and this has weight A prime, and you want these to be proportional. And similarly, you have cases for BCD by rotating this picture. And there's one more case where all these vertices are connected outside. So you want all of them to be connected outside. So you want to use these edges. So these are the three cases that show up to rotation. And you want the weight of this guy to be proportional to the weight of these guys. So the weight of this guy is 1, and you want it to be proportional to A prime C prime plus B prime D prime. And you want the same constant of proportionality in each of these. So some constant is what these are changing by as you do this move. So if you transform your weight such that you have this property, then if you look outside the little region where the move is happening, you don't see that anything has changed. So is there such a choice of A prime, B prime, C prime, D prime that gives you this, such that this is true, that if you look at any connectivity, the weights are just getting rescaled, and there is. So if you look at this expression over here, then it tells you that this delta has to be AC plus BD. And then if you look at these over here, then this tells you that A prime has to be A over delta, so A over AC plus BD. And if you look at this one over here, and you plug in this value of delta, you'll see that it is consistent, that this is still true. So this is the transformation rule. So you want to replace each of these edge weights with these ones. Okay, so this is the basis for the domino shuffling algorithm and things like this. You have this local transformation which is compatible with the dimer model. Okay, any questions about this? So now you want to rephrase. So these A, B, C, D are not well-defined coordinates. So you want to rephrase this in terms of the actual coordinates, these x variables, and see how these things transform. So initially you started with this picture where you have A, B, C, D. And the x coordinates of the various faces are, so here, so this is x0 is A, C over BD. And for these boundary faces, so this is, say, x1 is like 1 over A. X2 is B, X is 1 over C. So your initial x variables are these. So these are the alternating products that you would see. And once you replace it with a spider, you get these A prime, B prime, C prime, D prime. So here you have C over AC plus BD. And what are the new x variables? So the new x variable here, let's call it x0 prime, is going to be, so this is black, so this is white, is the alternating product where you're in the numerator if you're going from black to white. So this is B over AC plus BD divided by A over AC plus BD, D over AC plus BD, C, and these cancel out. And you see that this is 1 over x0, 1 over what it used to be. And you have similar formulas for the other ones. Let's look at one more. So what is the phase coordinate of this guy? So x1 prime. So x1 prime, if you compute the alternating product, so these are 1s. So 1 divided by this thing, C over AC plus BD, times 1. So this would be your x1 prime. And how do you write this in terms of the original x coordinates? So this is BD over C. So if I multiply this by A, then I have this. And now I divide by this, so I have and oh yeah, this is not 1 over C, this is just C. So since I'm going around this face like this, I'm going from black to white along this edge. So this should just be C over AC plus BD. And now I multiply and divide by A. And I divide by AC to get 1 over A, 1 plus BD over AC. And each of these is one of the original x variables. So this is x1 times 1 plus x0 inverse. And similarly, you can figure out what the other formulas are for how the other x variables of the phases transform. And notice that this is not the cluster mutation formula that we've been seeing so far. So these variables don't transform like cluster algebras. They have a more complicated transformation rule. And this is what is perhaps more natural from the point of view of the diamond model. And there is a relation between these cluster variables, the x variables, and the a variables that we've been studying so far. So anytime you have a variables, you can create x variables. By using the following rule. So if you look at, I mean, this works more generally for any quiver, but let's do it in this bipartite setting. So if I have a variables associated to each of the faces, so say E, and here's my quiver. So the general way to get x variables from a variables is that the x variable of a face, so suppose the face over here, is the product over all faces, number of arrows from, so suppose I'm looking at a face G, so G is going to be this face over here. So the number of arrows from F to G. So this is a general rule that comes from cluster algebras for how you're supposed to get x variables from these a variables. And if you apply this rule, so in this case, this will give you BD over AC. That's probably a bit misleading because I'm also using ABCD for the weights of the edges. Say again? Oh, yeah, A variables. Thank you. Yeah. Yeah. So there is this general procedure to produce X variables from A variables. And if you apply this procedure and you ask, suppose I know the A variables transform according to the cluster mutation formula, how do the X variables transform? Then you will get exactly this formula that we have over here, which we discovered by doing something completely unrelated, just by studying perfect matchings. So the X variables, which people discovered in cluster algebras, just naturally show up in this setting. Okay, so I think that's all I wanted to talk about. Any questions about anything?